We are going to end this chapter on permutation with a couple more results and some problems. So in the last class we found that any permutation can be expressed as a product of transpositions. So if sigma belongs to Sn, then sigma can be written as A1, A2, A3, A4 dash dash AP minus 1, A3. This is because any cycle A1 dash dash AN can be expressed as a product of n minus 1 n comma n minus 1 dash dash A1 comma A2. N minus 1 transpositions, product of n minus 1. And sigma is a product of disjoint cycles like this, so we can have like this. And this belongs to Sn. Now let us compute. Let us take just one transpositions. Let's say k comma j, and compose it itself. This is actually a permutation where only k and j are moved, and all others are same. So it is actually going to be like this: 1 k j n, 1 j k n. So you are composing with the same 1 k j n, 1 j n. So what happens here when you compose here? 1 k and k goes to j, j goes to k. J goes to k and k goes to j, and that will become the identity permutation. So any identity permutation, the identity permutation in Sn can be written as k comma j, k comma j for any k and j less than n or equal to just less than or equal to n. So you can write it as 1 comma 2, 1 comma 2. So identity permutation can be expressed as 2 transpositions. Because of this, you can say that the inverse of a transposition is itself, because you are multiplying the same thing and getting the identity map. Let us establish a result here. Theorem. Any permutation sigma in Sn can be expressed as a product of either even number of transpositions or odd number of transpositions, but not both. What I mean to say is we know that I is expressed as a product of two transpositions like k comma j, k comma j. So there are two transpositions here. So then you cannot express I as a product of 3 or 5 transpositions or odd number of transpositions. This is not unique. You can add to this as another one, 1 comma 2, 3 comma 4, 3 comma 4, etc. These are all representation of I, but it is all even. So either you can take this one or you can take this one. These are all same. You are talking about the same permutation here, but there are even number of permutations. So once it is found that a permutation can be expressed in terms of even number of permutation transpositions, then it cannot be expressed as a product of odd number of transpositions, and that's what I'm trying to say here. So the way we are going to prove this result is like this. Let's take sigma, a permutation in Sn, and any arbitrary transposition in Sn. Then our claim is the number of orbits on sigma and ij composed with sigma differ by 1. Meaning, if there are p number of orbits here, this will have either p minus 1 orbits or p plus 1 orbits. So that is what we are going to prove here. That is the first claim. Second claim is, so it's not a claim, actually it is a fact, like the identity map, identity permutation on Sn has n orbits. Now sigma can be written as a1 a2 dash dash a p minus 1 a p, assuming that sigma is product of p transpositions, and you can also write it as I. This I is the identity permutation, because if you are multiplying with you are composing with I, it remains same. So the difference between each of this computation, the difference of orbits between I and this is actually 1. So since sigma and I have fixed number of orbits, the product of a1 dash a1 a2 dash dash a p minus 1 p, it is also a, this is also a permutation, should have either even number of either even number of transpositions or odd number of transpositions. What I am trying to say here, let us say sigma has got 8 orbits, I has got a 15 orbits. Now we need to, once you compose this one, we need to get the whole thing in 8 orbits. So this has to, and each computation will either add or subtract 1 from here or add to this. So meaning the difference between this and the whole thing is 1. So when you count the number of orbits continuously, the total number of computation has to go lower by 7. Does not mean that there are 7 numbers here. It could be 9, or it could be either it could be 7, or it could be 9, or it could be 11, or it could be 13, like that. So everything has to be odd. And suppose this is 7, then this has to be even, and that is what I am trying to say here. So we will prove this result once we establish this sub result. So let us, there are 3 cases here. So what we are trying to prove here is the number of orbits on sigma and I comma j sigma differ by 1. Number of orbits. So what we will do is, there are 4 cases here. Case 1, case 2, case 3 and case 4. The first case is, this sigma can be expressed as a product of disjoint cycles. So let us first assume that I and j belong to same disjoint cycle of sigma. So because it is disjoint, it is commutative, so you can order it in any way. So what I am going to write here is sigma is equal to a comma I comma, let us say x1 dash dash x k1 comma b comma j comma dash 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 your y1 dash dash y k1 k2. This is something like here. See, if the cycle is 1, 3, 4, 7, 8, 9, and this is probably my I, and this is probably my j. See, this is not coming as a second item here, but you can always, this can be written as 3, 4, 7, 8, 9, 1. So that will become second one, and that's what I'm trying to say here. And these x1s are, this is x1. There is only one. So x1, x2, x3, xk1. So there is only one x1 here, and here this is actually my y1 and this is my y2. So that is what I'm trying to say here. Now we compose with the ij. What happens? ij a I x1 dash dash xk1 comma b j dash dash y1 dash dash yk2. See, besides this, there are a lot of other disjoint cycles here. But these are totally, because it is disjoint, well, while composing with ij and ij is included in this product is not going to be affected when you take the composition here. So this will be like this. So this actually is going to be, so from here onwards you don't need to worry about it. You start from here, from right to left. So A goes to J, A goes to I, and I goes to J, and J goes to Y1, dash dash, will go to YK1, YK2, and YK2 goes to A. So that closes it. Now the remaining is B. Okay, you can start with x1 also, but I'll start with C. But finally I'll reach x1. So B, comma J, and J goes to I, and I goes to x1. See, x1, I got x1 here, and k2, k1. Then again the same thing. So this is my sigma. And here, this is my product. So if you have P minus 1 here, you have P minus 1 here, but in here, this is split into 2, so there are 2 here. So totally it will be P plus 1. So when you compose ij with sigma, when I and j belong to same cycle, then that cycle will be split into 2. The next case is I and j belong to 2 different cycles. So what I will do is sigma is equal to bj y1 dash dash yk2 ai comma x1 dash dash x2 plus, I will have several of this. Here I and j belongs to different, I and j belongs to different cycle, and I can bring it here any way you want, but I want to bring it like this because these are disjoint cycles. So I comma j sigma is equal to I comma j b j y1 dash dash yk2, then a I x1 dash dash x2, then this. This what is going to happen is, you don't need to worry about this. So start from A goes to I, A goes to I, but there is no I here, but I goes to J. Now J is not here, J here, so J goes to Y1 dash 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 YK2, then YK2 goes to B, and B goes to J, and J goes to I, and I goes to X1 dash dash X2. So you are combining these two. So this is my sigma, and that is P. So this will have P minus 1. Case 3 and 4. Case 3 is actually I belongs to a cycle and J is a singleton. That means it goes to itself. So what happens here? This will be I comma j is equal to a1, say a comma I comma x1 dash dash x2 xk1. Then somewhere you have an I here, but I am going to bring it here, j. And you have several of them. So we'll start from here. So this will be equal to j, and j goes to, there is no j here, j goes to I, and I goes to x1 dash dash xk, xk1, and xk1 go to A. So what you are going to do is you are combining these two together. So this will have P minus 1. And the last situation is case 4, both I and j are singleton. So sigma is equal to a1 dash dash ap, then there will be I here and there will be j here and dash dash. So once you compute with I comma j, what will happen is nothing is going to change except that you are going to join these together. So ij, then a1 dash dash ap dash dash. That means you are combining these two together, so this will have P minus 1. So if sigma has P orbits or P disjoint cycles, then I comma j contains either P minus 1 or P plus 1 cycles or orbits. And that is exactly what we are looking for here. Once you get that, then we have the result. So this results causes two definitions. A permutation sigma in Sn is an even permutation if it can be expressed as even number of transpositions. It is called odd number of transpositions. It's called an odd permutation. It's called an odd permutation if it can be expressed as odd number of transpositions. For example, I is an even permutation. So our next result is the number of permutations of number of even permutation and odd permutation in Sn are same, and is n factorial by 2. So this is a very simple result. The proof goes like this. Let's tau is equal to any valid transposition in Sn. Let's take ij. Then define a map phi from Sn to Sn by phi of psi is equal to tau of this is a valid map. The claim is phi is bijective. Please verify. Now, when sigma is even, then phi of sigma is odd, and sigma is odd, then phi of sigma is even, because of the definition, because the number of transpositions differ by 1. And that implies number of even transpositions, number of even permutation is equal to the number of odd permutation. And because Sn has got n factorial, each of them will be n factorial by 2. Now let us introduce a very important subgroup of Sn. So the collection of all even permutation in Sn forms a subgroup of Sn under function composition. Okay, how do you prove a subset is a subgroup? We need to prove that the binary operation is closed. Then we need to prove that there exists a identity, and we need to prove that for every element there exists an inverse. So here let sigma 1, or first let us say let An be the collection of all even permutations. So let us take sigma 1 comma sigma 2 belongs to an, and that implies sigma 1 and sigma 2 are even permutation, and so sigma 1 after sigma 2 is an even permutation. And that implies sigma 1, sigma 2 belongs to A. So that means the binary operation is closed. Here, the identity map of Sn is an even permutation. Because I is equal to 1 comma 2, 1 comma 2, and that implies I belongs to A. So there exists an identity. Now, for every element there exists an inverse. So that implies let sigma belongs to An, that implies sigma is a even permutation, and that implies sigma is equal to a comma a1 comma a2 dash 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 a p minus 1 p, where p is odd. Because when p is odd only, this will become even. And that implies sigma inverse will be ap minus 1 ap inverse dash 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 a1 a2 inverse. The inverse of all the transpositions are same. So this is going to be ap minus 1 ap dash dash a1, where p is odd. And that implies sigma inverse belongs to A. If you have p minus 1, if you have p minus 1 transposition on sigma, you have the same number of transpositions in sigma inverse. So sigma inverse belongs to A, and that implies An is a subgroup of Sn and is called alternating group. Now let us do a problem. Find maximum order of an element in S5. S5 is the symmetric group on 5 elements. So the elements in here are permutations. So what we need to do is, if sigma belongs to Sn, S5, then the order of this actually is the lowest number k, such that for sigma to the power of k is equal to I. The way we are going to do this one is split this one into disjoint cycles. One result we need to assume here is that the order of the product of disjoint cycles is the LCM of the order of each of the disjoint cycles. What I am trying to say here is, let us take S3. So let us take S3. So let us take one permutation here. That is 1, 2, 3, 2, 1. Sorry, 2, 1, 3. So the disjoint cycles are 1, 2, and 3. So the order of this is the LCM of the order of this and this. So the order of, so see what is order of here? See sigma square 1, 2, 3, 1, 2, 2, 1, 2 and 3. So the order of sigma is equal to 2. Here the order of this is 2. Why? Because 1, 2 times 1, 2 is equal to I. So this is actually 2. And this is 1. This is actually the identity map itself. So the LCM of this is 1 times 2. Sorry, the LCM of 2 and 1 is 2. So if you express a sigma in S5 as a disjoint cycles, then find out the order of those disjoint cycles and you find a LCM, and that is what we are trying to prove here. So let sigma 1 dash dash sigma k be disjoint cycles of sigma, meaning sigma equal to sigma 1. This has to be disjoint, okay? So sigma 1, sigma 2 dash dash sigma k. Then the order of sigma is equal to, or you can say the order of sigma is equal to the LCM of order of sigma 1, order of sigma 2, order of sigma k. Our aim is to find out the maximum order. So we are reducing the complexity of finding the order of an element to the order of the cycles. Now what are the length of the cycles here? You can have a cycle like this in Sn, or you can have a cycle like this in Sn, or you can have a cycle like this in Sn, in S5, sorry. Or you can have a cycle like this. So, a permutation in S5 can be either written as sigma equal to 1, 2, 3, 4, 5, because that's the whole thing. Then we can also written as 1, 2, 3, 4, 5, or you can written as 1, 2, 3, 4, 5, or sigma 1, 2, 3, 4, 5. This is the only possible ways of handling this. And because this is commutative, this is the only way. And what is the order of this? So if you take this one, 1, 2, 3, 4, 5 means this, what does this mean? 1, 2, 3, 4, 5. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. So this will be, the order of this one will be 5. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, and 5 goes to 1. So next time it will be 1 goes to 3, and the next time it will be 1 goes to 4, next time it will be 1 goes to 5. So the order of this will be 5. The order of sigma will be 5. There is only one cycle here, so there is no need for an LCM. Here this is always 1. Whenever there is a singleton orbit, it's always 1. And here this will be 4 times 1. It's actually the LCM of 4 and 1, and is equal to 4. Here it will be LCM of 3 and 2, and that is 6. And here it will be LCM of 2, 2, and that is equal to 2. So the maximum order is of order 6. So the maximum order of an element in Sn is 6. So we will do the last problem in this session, and that is let Hn be a subgroup of Sn, then all the permutation in Hn are even, or half of them are even. So see, Hn is a subgroup of Sn, and that implies I belongs to Hn, and that implies Hn contains an even permutation. because I is always an even permutation. Now, suppose Hn has all even permutations. We know that there is one, but suppose that everything is even, then we are done. So assume that sigma belongs to Hn be an odd permutation. Then what we do is, just like we did earlier, define a map phi from Hn to Hn by phi of sigma. Let us assume that this is mu. Sigma equal to mu of sigma. So phi is a bijective map. And when sigma is even, then phi sigma is odd. When sigma is odd, then phi sigma is even, because of this map. And that implies phi, that implies the number of odd and even permutations in Hn are